Kupke of the University of Russia.
Okay, so thanks a lot for the introduction, and thanks a lot for giving me the opportunity to talk here. So my talk will be, luckily I'm the last speaker today, so my talk will be probably the most basic, but on the other hand, maybe also not necessarily most of the audience is used to what I'm going to talk about, so maybe in that sense, we'll see what happens. So the question is it related to categories, logic, and physics? Well, it's related to logic for sure. I put one diagram today in the morning, so in some sense it's related. I realized though that I forgot almost to use XY pick properly, so that means something bad, I guess. And then the last thing, is it related to physics? Well, it contains topology, so in some sense it is related to physics. And I can also make this a bit more precise, but really only very much a bit. Okay, let's see. So I'm going to talk about the mu calculus, and the particular semantics for the mu calculus, where we interpret formulas over Kupke frames. So the modal mu calculus. How many people are familiar with the modal mu calculus here? So I'm going through the definitions anyway. Okay, it's no consent with this video. But we'll see. I'm going to talk what we want to do, how we want to change the semantics, and I'm going to tell you how to characterize the semantics with games. And so the main result will be, in fact, that these games exactly characterize our topological semantics. This sounds just now all very high level, but we'll come to this in a second. In the end, I also mentioned bisimulations. It's not so important. First of all, before I start, a disclaimer: topological semantics for the mu calculus for us means, so us is, by the way, not just me and my imaginary friend, but Nick Visionishvili from the University of Amsterdam. So topological semantics for us means we have a Kupke frame where we have topology on it. There are other people who interpret modal logic directly on a topological space, where the modal operators are interpreted as interior or closure. And there's some very recent work on this by Rob Boltblad and Ian Hodkinson, but this is not what we are doing. So this is like a volume of more than 100 pages, I think. So if you want to know more about the interpretation of the mu calculus in terms of interior enclosure, this is your friend. So first of all, what is the mu calculus? Let's go back to this one. So it's just basically modal logic. So modal logic just has propositional logic plus two operators, box and diamond, and they are interpreted on relational structures. A relational structure is just, in our case now, a set with a binary relational. And this symbol here is to be interpreted as phi holds in the successor of the state. And this here means phi is true in all successors of the state. So basically this line here is modal logic, basic modal logic. Problem with basic modal logic, if you wish, is that you only can look finitely many steps into the model, because you can only write finitely many diamonds or boxes in a formula. If you want to express properties of the ongoing behavior of the state, you add the fixpoint operators, the mu and the nu. And the mu is the least fixed point, and the nu is the greatest fixed point. Condition is that if you write mu p, the p only content is here without negation in front. So you see, I pushed the negations already to the propositional level, and then the condition here is just that p is only allowed to occur for the money to count negations to be safe. Basically, even number of negations. So what are the so I said these are fixed points, but the question is fixed point of what? And so let's see. For a formula in this logic, and for a Kupke frame, and for evaluation. So basically we have to say, how do we evaluate variables? We can define an operator on the lattice of predicates, so the power set of x. And so this operator just maps any subset of x to the semantics of delta, where we interpret this variable p with this predicate. So we just look at formulas now as operators on the lattice of predicates. It's a complete lattice. That's why we can say what's the fixed point, the least and the greatest. That the least and the greatest fixed point exists, and we also can compute it. So this is all very standard. And so the point is indeed that if delta only contains positive occurrence of P, then this is positive. And this is monotone, and therefore we can get a fixed point. So here's an example. This is a model where we have just the natural numbers, where the relation just always is the predecessor, and you have one point infinity where you have a reflexive error. And so the standard interpretation of the root calculus would now say, okay, we have this transition relation here. We could define this formula, mu q p or diamond q, which I've said here already, this is kind of diamond star of p. And so this just means p is reachable via the transitive closure of R. How can we see this? Well, basically, we just have to look at this formula. This formula corresponds to the operator which maps a set to the set of all states where P is true, or those states which see an element of U. And if you generate the least fixed point, how do you generate the least fixed point? You start from the bottom of the lattice, which would be the empty set. So you would put here the empty set, you map it to VP union diamond empty set, which is just VP. So in the first iteration, you just get the states where P is true. In the second iteration, you get the state where P is true in one step, and so on. In the end, you will get, in this model, all the natural numbers as the least fixed point without the state. So this is what happens in the root calculus. Now what we were looking at, and I'm going to motivate this, I hope, but let's just say what we would just look at this with the topology, where we have a basis of clopen sets, which are the finite subsets of the naturals, or the cofinite sets containing this infinite set. And then we're not interested in the least fixed point, but in the least clopen fixed point. And in this case, the least clopen fixed point would be just everything together with this thing. And so the idea is here that P, this formula would then express that P is reachable via the topological transitive closure of R. So what we get is some kind of notion of reachability in the limit. Because it's kind of, so the example is not very realistic, obviously, but so if we can reach P from all the ends, then we should also say that we can reach it from the limits of P. This is. But why are we interested in this in the first place? So the first motivation is indeed just, okay, if we do logics on topological spaces, I think this notion of reachability in the limit could be the natural one, because if you say you can reach it from all the states up to a certain point, then you should be also saying we reached from the limit, basically. So in a way, this seems to be a natural notion of reachability for systems with continuous behavior. It's debatable, but that's one of the motivations. The other motivation is less debatable, but also did not yet work out. So the other motivation is basically we want to apply techniques from stone duality to the mu calculus. And more generally, we want to get a completeness proof for the mu calculus, which is really based on duality theory rather than on a lot of very difficult combinatorics without too much understanding. I should say this is, of course, an offline remark. Okay, so our goal is, in this talk, just, so this is the motivation with semantics. The one thing reachability in the limit, the other one completeness proofs via duality. And in this talk, I'm going to just talk about how to characterize this semantics, which I'm going to define properly in a second, using games. And ultimately via automata. So why are games important? But just give me one more slide to argue for this. So suppose we have a formula, for example, in the Mu calculus, where we have already two fixed point operators, mu q, diamond, brackets, S and P or Q. Now if you remember that semantics, when you have to compute all the, in order to compute this greatest fixed point, you have to compute all the approximants for the greatest fixed point. Basically, to get to the greatest fixed point, you start with the top element and then you apply the operator until you reach the fixed point. But in order to compute the approximate, each time you also have to compute the least fixed point. So you get really like an infinite sequence of infinite sequences in a way. So in this case, it's not too difficult, but you can see if you get lots of nesting of fixed point operators, it's getting rather tricky to understand what the formula actually means. It's a practical thing. On the other hand, if you know, V2 for fixed point logics are usually automata. And the semantics of automata is based on exactly the game semantics rather than on the semantics in terms of the monotone operators, which I just showed you. So in the game semantics, we look at this formula and we look at it as a model, on a model, and in order to see whether the formula is satisfied, we think of a game between two players where the one player says the formula is satisfiable, the other one says it's not satisfiable. So the player who wants to satisfy it, for example, if he reaches a diamond, has to provide a successor which satisfies this. And then if it's an OR, he can choose. If it's an AND, then the falsifier can choose, and so on. We come back to these rules in a second. The main point is that in this game, if we have fixed point operators, if we reach the variable, then we unfold the fixed point. And so the semantics in the game requires that the outermost fixed point, which is unfolded infinitely often, has to be mu. Then the game is won by the verifier and not by the falsifier. Otherwise, falsifier wins. And so if you want to win this game here, you have to make sure that you do not stay in a Q loop for infinite number of steps, but you only have to stay in Q if you reach states where S is false. So whenever there's a state where S is true, you can jump to this side of the disjunction, go here and unfold the mu. If you by any chance end up in the bad situation that you never reach a state where S is true, you always have to unfold the mu and you lose. And that's why this formally expresses there's a path along which S holds infinitely often. This is just. So I said, so this is what you see relatively immediately if you know the game semantics. It's more tricky with the indentation semantics. And in addition, the game semantics is really the backbone of all the automata theory for the Mu calculus. But here's an obvious problem. The game operates on states of the model. How do we ensure in the end? So admissibility. You remember I hinted at this, I didn't do this yet formally. We want to interpret the fixed points not as arbitrary fixed points, as arbitrary subsets, but we want to have clopen subsets as the fixed points. And so if we argue that in the game, we argue state-wise, and we have to ensure that wherever we go, the winning positions of this game has to be still a clopen subset. And so this is the issue that we had to address somehow. That the game operates on the states, but you want to have that the collection of all states somehow are admissible. There's a whole lot of related work. This goes back to the 90s. People already in the 90s tried to prove that completeness for the Mu calculus in a duality-based setting, and they proved completeness, but it's well known that there is some kind of problem. Basically, they prove completeness, but with respect to the wrong semantics. So they prove completeness with respect to the general frame semantics, which is kind of clear. But still, I mean, there are lots of interesting aspects in these papers. And so this semantic of admissibility has been studied recently in several occasions. I don't want to go through this in detail. Let me just mention that completeness for the normal calculus is still a very active topic, just because the original proof was so complicated. And so there was a paper last year by these people here who kind of reproved and analyzed the Walukiewicz's completeness proof. And so succeeded in doing so and generalized it to all kinds of coalgebras. But even more recently at LIX this year, there's also a paper about the topic by two totally different people who seem to have maybe yet an even easier argument. So anyway, I just wanted to say this for showing that this is kind of an active area. The question I have to you is, do you know what I mean with completeness? Probably not. Completeness means that we want to have an axiomatization of the mu calculus, and a complete one means that whenever a formula is consistent with respect to this axiomatization, there must be a model of this formula. This is what completeness means. It has nothing to do with the completeness of the lattice of power set and so on. I realized that the notion completeness has at least two meanings in my talk.
And you don't mean that for every element in the model there's a formula that takes it out?
No. I didn't even know that this could be called completeness, but I'm sure you could indeed. So I realize now, while talking through this, that I should have mentioned this a bit earlier. So what's our setting in the first place? So we are based on 15 frames with topology. And the topology is unfortunately not just a stone space, but it's what's called an extremely disconnected stone space. So what's extremely disconnected stone space? So stone space is a compact Hausdorff space with a clopen basis. Extremely disconnected means that the closure of any open set is again open. And if you think about it, that also means that it's also then clopen, because it's closure and it's open. But much more basic, you could just say that you want that the clopen sets form a complete lattice. And for those of you who followed my ramblings just now, it should be clear why we want to do that, because in a complete lattice, we always have the fixed points. And much more than that, not only do we have the fixed points, but we also can approximate them from the bottom element up and from the top element down. And in fact, this way of computing fixed point is in a way the backbone of game semantics. Because, so that's why we do this. If we drop this, then it's unclear how to define game. I mean, you could just say, so, yeah, that will come up in a second, basically. So this is really the backbone, because of game semantics as intended in my talk. I'm not saying the game semantics as, the problem is the terminology of game semantics obviously might mean a lot of different things. I'm just meaning now that game semantics for mu calculus here. I'm not saying that it's the backbone of game semantics in general. Okay.
So you're saying that having these kinds of spaces is sufficient?
Yes.
That is also necessary?
Yeah, so that's the question. How we would go beyond, want to go beyond this. So, it's basically necessary to understand, well, the answer is basically I don't know whether it's necessary. To be fair, I think. I could say it's necessary for me at the moment. Which is a very local definition of necessary. But yeah. We could fit, yeah, no, let's continue with this. So the clopens form a complete lattice. This is exactly the condition, in fact. And so the frames we're looking at are descriptive frames, which have such a space as a carrier and a relation R, which satisfies certain properties. It satisfies the properties that it satisfies two properties, in fact. One is that R has to be continuous in a certain sense. Namely, so what we need is that this thing corresponds to a Vietoris coalgebra. But what it just means is that this has to be indeed continues with respect to, it's a map from X to the Viennent space over X. I'm not going to discuss this in detail. We can discuss this in many details afterwards if you want. One thing is that the successor set for every X has to be closed. Because the Viennent space is exactly based on the collection of all closed subsets. If you know the Viennent space, so it has to be closed. So it has to be point closed and it has to be continuous in the right sense. And the model in our sense is just this thing together with a clopen valuation. It has to be clopen obviously because if you don't have the propositions are clopen, how could anything else be clopen? So that's obvious. How much time do I have all in total, by the way?
We started 10 minutes late, but the schedule says we could publish 7 minutes.
I see. Anyway, so I have to stick to the schedule. No, not to the schedule, but to the 10 minutes. So for the purely model formulas, indeed, we ensure that they're clopen by just making sure that the valuation is clopen. And by the fact that we are on descriptive general frames. So the fact that this R satisfies conditions means immediately that for all the modal formulas you can write down, the denotation will be a clopen subset. But for the fixpoint operators, we have to note basically that this thing will be done monotone operator on clopens. This is a complete lattice, so we can again interpret it as the least and the greatest fixpoint. But now the least and the greatest clopen fixpoint. And indeed here it's on one slide. How do we compute the fixed points on a lattice, on a complete lattice? Well, for the least one, we start with bottom, and then just apply the operator until we reach limit ordinal, where we take the join. Similarly, for the greatest, we start with top, apply the operator until we reach the limit, where we take the mean. And then you know from general theory that indeed any monotone operator, we have ordinals where we reach this fixed point. I skipped this slide just to make a headway. If you want to know why we think that extremely disconnected spaces are related to completeness, I can go back to that one slide where I had a diagram. But let's just go to the fixed point games right now. So all talks here are indeed two-player games played on a graph. And the players are called Eloise and Abelard. You can think of them as the verifier and the falsifier. And the board position are just partition and positions for either Eloise and Abelard. And plays can be infinite. The winning condition on infinite games can be encoded using a parity condition, although I don't really care about it. So I will just tell you now what the winner will be. In the end, what we're interested in are parity games. But this means in particular that in any position of the game board, either of the player has a history-free winning strategy. So that each of them has a either of the players, so one of the players will have a winning strategy, and it will be history-free, so only dependent on the current state. I'm not going to really go into why this matters, but it is again at the heart, so that's why I stress this anyway. So how are these sequences related to games? Right? The approximation of fixed points. So recall if we are on the power set lattice, we know that the meet is just the intersection and the join is just the union. Then we can just define one game which basically characterizes least and greatest fixed point. It's the following one. So we're given a monotone operator, capital F. We want to check whether a given state is an element of the fixed point. So Eloise claims it is, Abelard claims it isn't. So what Eloise does is Eloise has to provide like a proof that this is an element of the fixed point. So she has to provide a subset such that X is an element of F applied to this subset. And then Abelard claims that this is wrong somehow. And then he can point to the mistake. So he can just pick one out and say, here you missed something. This is the game. And so the least fixed point, so the rules are always the same. In the least fixed point game, so whoever gets stuck, so if Eloise couldn't find any such C, for example, she gets stuck, so she loses the game immediately. Similarly, if Abelard cannot pick anything, he also loses immediately. But for the infinite plays, in the least fixed point game, Abelard wins the infinite plays. So if he can ensure that the game goes on forever, he wins. In the greatest fixed point games, it's Eloise who wins if she can go on forever. And then you can indeed show that Eloise is a winning strategy in position X in the least fixed point game, if and only if X is in the least fixed point. So let's see, and similar for the greatest fixed points. Let's just briefly see. There's just one thing counterintuitive about this, right? Because that ordinal, which computes the least fixed point, can get really huge. But the game will be, I mean, she only wins the game if she can win infinitely many rounds. So that is just this old phenomenon that well-foundedness of the ordinals can be slightly funny at times. Anyway, so this is...
So you say finite, did you mean finite or finite?
Finite. I mean, it's just basically... Sorry?
I think I got the one.
So let's just see what happens for the fixed point game. Suppose Eloise is right, so she has a state in the least fixed point. This means that there is some ordinal, it can be huge, but there is some ordinal that says X is in the alpha approximant of this fixed point. So if alpha, for example, is a limit ordinal, then X will be in this join. So what she's going to do is, she will in fact move to this set here, because she knows that X is in F applied to this. So the union over all the smaller approximants. And then Abelard cannot do anything else but picking something from here, which will be now in the approximant of a smaller, sorry?
I just realized why it's funky money, yeah.
Yes. Thanks for having the appropriate reaction. That's what I was hoping for.
No, because you said it, yeah, should we say, what? Yes. You said it.
Yes. So basically you just go down now to a smaller ordinal, and now the game continues somewhere at the smaller ordinal, and by induction we can already assume that from here onwards Eloise will have a winning strategy. Similarly for successor ordinals. And so indeed, so the well-foundedness means that either Abelard gets stuck at some point, or basically it just means that Abelard will get stuck at some point. And then for the converse, just assume that X is not in the least fixed point. Then either Eloise gets stuck immediately, or she moves to some C, which X is an F of C. But then we know that this cannot be a subset of the fixed point. So Abelard just again moves to something which is not in the fixed point, and then we just more or less again at the position where we came from, which means that either the play will be infinite or Eloise gets stuck. Which shows that Abelard has a winning strategy. Now we just do the same game on fixed points on extremely disconnected stone space. The main difference is just that the join, the meet here is just not the intersection, but it's the interior of the intersection. And the join is not the union, but the closure of the union. This is the main difference. And then you can think about possible, let's just focus on the mu game here. So this is kind of the thing which is relevant for the mu game. I'm always a bit afraid of this paragraph because I'm confusing myself usually with it. Let's see. So the possible consequences for this mu game are as follows. In order to show that X is in the least fixed point, it suffices for Eloise to provide a suitable set C, such that X is an F of U for all the clopens containing C. Why is that? Because, in fact, this is exactly how you do the closure in these stone spaces. Just take the intersection of all the clopens which contain that set and you have the closure. And that's why this intuition corresponds very directly to what's written there. We could also demand, of course, that Eloise chooses this set, the full thing, but then Abelard is only allowed, so she's rather not choosing this set, but she's choosing this closure of O, and he is only allowed to challenge her on elements which are in here. So we have to make sure that if she has to pick this full set, then he has to be forced to somehow pick something from in here anyway. And so both observation leads in fact to different games. The one game is the first one, where Eloise moves to some arbitrary set C, such that X is in F of U for all the clopens containing C. And then Abelard indeed just picks an element. That's the one game. And the other game would be she's moving to a clopen set such that X is in F of U. But now Abelard is not allowed to pick just an element of the clopen set because he could pick somehow an element of the edge of the clopen set. So he has to come up with another clopen set which has a non-empty intersection with the original one. And then Eloise picks an element from the non-empty intersection. In that way we make sure that wherever we continue, we continue kind of in the interior of where we started, not really in the, not at the edge. That's important. And the reason why this for all that exists is here. It's just to keep bookkeeping because we want to keep the positions for Abelard and Eloise disjoint.
What is keeping Abelard from choosing U prime as U?
Let's keep it over to prime as U.
Why can't he go to the boundary?
Well, he can choose the full U, but then in the end Eloise is still, I mean, the bigger he makes it, the better for her because she will move away from the only important thing is really that whatever he chooses contains something which is not in the boundary, and this is what Eloise is going to pick. Yes, that's true. Yes. So the correctness, let's just see if one of these games, suppose that X is in this least clopen fixed point for some X, then there's some least ordinal before, then we have to show that Eloise has a winning strategy. It ensures that either Abelard gets done, or that the player reaches a position with some smaller ordinal. And so indeed Eloise will just move from X to this join in this limit ordinal case, which is of the form closure of the union. And if Abelard doesn't get stuck, he has to move to some U prime, such that this U prime has a non-intersection with this closure. But then because this is a clopen set, it will have a non-intersection with this set. And therefore Eloise can just pick an element from here, and we continue indeed with something which is smaller. And so why two games? So the pragmatic, so unfortunately and fortunately at the same time, we need both games in our argument. But I don't have a formal argument for why they are really, really necessary. I can just say that this makes the arguments work, and there seems to be no direct transformation of winning strategy from the one game to the other game. So the point is, these are just the fixed point games. We want to have a game for the formulas of Lie calculus. And now if you go to this big game board of this game for the formulas on a model, you have to somehow at some point transform winning strategies on this evaluation game to winning strategies in the fixed point game. But it's difficult to come up in general, coming from this evaluation game, we have to equip Eloise with a winning strategy in the fixed point game of some sort. It's difficult to say that we have a clopen subset somehow that we can cut out of this evaluation game. It's surprisingly easy on the other hand to say we can just take a collection of states from this game board such that whenever we would take a clopen which contains this collection, that property would be true. So therefore, moving from the evaluation game to the fixed point game, this is the thing we want, and vice versa, if you want to go from the fixed point game to the evaluation game, for some reason it's easier to start with this one and then transform the strategy here to the evaluation game. That's why we need both of these games. And similarly, in fact, we have two games also for the greatest fixed point, which are curiously, so this is the analogous one from the version 1, so she chooses a C such that X is in F of U for all the clopens. The interior of C is a subset of U. But this one is slightly different. but it just looks different. It's just really, really switching quantifiers. But if you switch quantifiers, remember in the previous game we had a choice by Eloise followed by a choice by Abelard followed by a choice by Eloise. Now in this game, Eloise and Abelard switch roles here. So you would have 2 moves by Eloise and 1 move by Abelard. And this 2 moves by Eloise can just be compressed into 1 move. So this one looks surprisingly simple, right? It's just x and x. She moves to a clopen and x is in F if you Abelard moves to an element. And so the goal indeed was that we wanted to have a game such that for a given formula phi and a model, define a game such that Eloise has a winning strategy at this position phi, comma, x. The positions are formulas, comma, element states in the model, if and only if x is in the denotation. This was the main goal. Reach this slide that we made in the talk. So anyway, so here is the game. If you know the game for the mu calculus, this is just exactly what happens in mu calculus. For example, if p happens to be a variable and x doesn't make p true, then this should be a position of Eloise where she cannot do anything. Because p is false, we are in the position where p, but she claims p is true, so she should lose. All those are exactly the same. For and, Abelard can choose, for or, Eloise can choose, for diamond, Eloise can choose a successor, for box, Abelard can choose a successor. In this position, nothing happens, we just chop off the fixed point. And if we have a bound variable, so this is the standard game. Then basically we just unfold the fixed point, and nothing happens. This would be the game in the standard semantics. Now we just have to do something when we unfold the fixed point operator. So instead of just unfolding the fixed point operator, in position px, if it's a mu variable, then Abelard has to give Eloise more choice. So he has to give her a clopen. Symmetrically, if it's a mu variable, then Eloise has to provide the clopen. And then basically the game just continues. So now just before we unfold the variables, we just have to, one of the players has to make the choice bigger. So it somehow introduces some fuzziness at that point. And then indeed, the other player can pick an element of this thing. And so the intuition is indeed that mu should become easier to prove for Eloise, as we saw in the very beginning example with this line, because the reachability was reachability plus the limit. And so that's why he has to provide more choice for Eloise, so to speak. Similarly, safety will become more difficult for Eloise to prove. That's why she has to provide more choices for Abelard. Okay, I just now reached the end of this talk. We can also do something about bisimulations, where we just say, in addition to just saying it's a bisimulation, we also have to assume that it's clopen, meaning that indeed Z of a clopen, image of a clopen set and the relation is again clopen and vice versa. And if we have this condition, then we can also prove that this semantics is just invariant under bisimulations. And so this was just an initial application of just using the fact that we now have games. Normally you want to have games to prove something. But there's lots of questions attached to this. But first of all, extremely disconnected spaces have the justification, but I would prefer to go, for example, to compact spaces and take the regular open sets. I also have a complete lattice there. And this seems to be more natural in terms of this reachability-in-the-limit example. Not so much about completeness for the calculus. Indeed, in another notion of admissible subsets, so you could also think of measurable spaces, measurable sets. Well, you need to develop automata based on this game semantics. And indeed, related to this shed light on the completeness of the calculus. And if this or parts of it could work out, one can of course generalize this to algebraic variance, and that's my talk. Thanks.
Questions?
You have this formula at some point where you can interpret it as there's a path along which there's S is infinitely often true.
Yes.
That was easy to see in the game-theoretic semantics.
Yeah.
Are there also formulas that are not so easy to see with games, but easier in the other semantics?
I don't think so, but no.
So games are just the answer to everything.
No, I mean, games are not the answer to everything, but I would just say that games are generally easier because games take care of this alternation of fixed points. If there is no alternation of fixed points, then the semantics is relatively easy anyway, in both senses. So I do not believe that there's an example, unless it's kind of a trivial example, like UXX. It's easier in the denotational thing because you immediately see that if you start generating from empty set, it's empty set. But other than that, I don't know. I don't think so. Yes.
So you pointed out that the motivation for this work is to reason about systems with continuous behavior.
Yes, I made this good claim indeed, yes.
So when do you expect to apply your research to the systems?
Basically, as soon as I now finally go to compact Hausdorff spaces rather than staying in these slow spaces, would be my answer. But I don't know when. I was hoping that we would have done it already, but we didn't do it yet. Maybe next week, because my co-author will be here next week. No, but more seriously, I don't know, basically. But we just have to go to different topological spaces. Because at the moment, the setting doesn't work for this aspect.
How far is this work from the game semantics of Dan Geka from Birmingham? Because that's very practical.
But these games are very different. The only answer I can give is that as far as I know, these games are different.
All right, okay, that's good.
Meaning, I don't think Dan Geka's games are about new calculus. This is probably more in the style of game semantics, Abramsky and Luke Ohm and so on, I would think. And this kind of games I don't know very well.
All right, thank you.
But for example, in these games, as far as I know, there's no winning and losing. So they're using games, but they're using very different games.
Well, that's computing.
Yes. Games just give you some operational semantics of something. And as we have formulas here, this operational semantics has to be talking about winning and losing because the formula has to be true or false. And if you give semantics to a program, then true and false is not the answer, I guess. Yes.
Okay, if that is the last question, then we will wrap up for the day. Thanks very much, Clemens.